In this video, I'll explain how virtual machine objects are stored in a vSAN data store. And so let's start with the very basics. What is each virtual machine made up of? Now, if you're familiar with vSphere, you're probably familiar with the fact that every virtual machine has a set of underlying files, like VMX file and log files and VMDK files and so on and so forth. Well, all of those same constructs still exist here with vSAN. But the way that these objects are actually stored on vSAN is we have what's called a VM home namespace. This is the VMX file, the log files, and other metadata specific to each virtual machine. That's stored in the home namespace. The VM swap file, that's the swap file. Now, this is created when a virtual machine is powered on, just in case there is memory contention on the host. The VMDK, that's the virtual disk of my virtual machines. And the snapshot delta VMDKs are created whenever a snapshot is taken of a virtual machine. So we have all of these objects that have to be stored for a virtual machine. And so how do we ensure that these objects are stored in a manner that is reliable and redundant, and that we can actually tolerate a physical failure of an ESXi host? So let's take a look at a VMDK in particular. That's the object that we're going to look at right now. So our virtual machine is VM1. And if we look here on the far left, we've got this VM called VM1. And when VM1 is stored on virtual SAN, one of the objects is going to be the VMDK object. So we're going to have a VMDK right here. Now in this situation, we have designated that the primary failures to tolerate equals 1, and we're using RAID 1. What does that mean? Well, basically what that means is we need to be able to tolerate the failure of an ESXi host or of a disk group. And so here you see a mirror copy of that VMDK that exists on a second ESXi host. That's failures to tolerate equals 1. So we have mirroring of this VMDK object. This is an object-oriented file system. We almost have to think of each ESXi host as like a disk in a RAID array. So if you're familiar with RAID, you have multiple disks, and the data is mirrored across those disks just in case a disk fails. This isn't really RAID. This is more like RAIN, redundant array of inexpensive nodes. Now my data has to be mirrored across ESXi hosts, just in case we have an ESXi host that fails. Like for example, if ESXi 03 were to fail, we would still have an intact copy of the virtual machine's data on ESXi 02. So that's number one. That's one of the ways that these objects are stored. And I can have a storage policy that dictates this. That's how I'm going to set this up. So I'll create a storage policy that dictates this virtual machine needs to have one primary failure to tolerate. The other object that is created automatically in the background here is the witness. And the witness is essentially a tiebreaker. Right? It doesn't have any actual application data. It's a tiebreaker. So for example, if there is some sort of failure that, let's say, isolates host ESXi 03 from the rest of the network, maybe both of these VMNICs fail, there is a mechanism to kind of have a vote here and say, hey, I'm the witness, I have one vote. This copy of the VMDK, I have another vote, majority wins. This is the active copy of the VMDK. That's what the witness is there for. It's specifically a tiebreaker. And we'll go much deeper into this when we get into failure scenarios later on in the class. Okay, so given the fact that we've set a storage policy that dictates we have RAID 1 and primary failures to tolerate is set to 1, we need at least 3 hosts. We need a witness on one host, one of our replicas on one host, and another replica on another host. And by the way, that's what these guys are called. So notice there are two identical copies of VM1 VMDK. Right, these are exactly the same. They are replicas of each other. So each mirrored copy of data is called a replica. So let's take a look at a little bit different of a scenario. So when primary failures to tolerate was 1, I needed a minimum of 3 ESXi hosts. 4 is better, by the way. 4 is better. Let me just talk about that for a moment. 4 hosts is better in this scenario, and that's why I have a 4th host shown here. Because what if I need to take one of these hosts down for maintenance? That's a little bit problematic if I only have a 3-host cluster. So having that 4th host there is definitely beneficial, but technically you only need 3 hosts for primary failures to tolerate equals 1. If we change that to primary failures to tolerate equals 2, now we need a bare minimum of 5 hosts. We need to be able to lose any 2 hosts. You can see at the bottom of the screen here that if I have a 100 gigabyte virtual disk, it's actually going to consume a total of 300 gigabytes of raw space. So why is that? Well, I need to be able to tolerate 2 failures. So here you can see we have 1 witness on one host, a second witness on another host, and then we have 3 replicas. In this scenario, I can tolerate the failure of any 2 objects, and my virtual disk will still continue to function. Like for example, if ESXi02 fails and ESXi03 fails, I still have an intact copy of that replica on ESXi04, and we can have our little vote here. 1, 2, 3, majority rules. So that will be the active replica. So I have to have at least 5 hosts in my cluster if I plan to use primary failures to tolerate equals 2. And I'm maintaining 3 mirrored copies of that data, so it now consumes triple the space. If we go back to the last slide, when our failures to tolerate equaled 1, we can look at the bottom of the screen and see here a 100 gig object in this scenario is only consuming 200 gigs of space. So there's no such thing as a free lunch, right? That's the moral of the story. If I want more protection for my data, it's going to consume more space. I can even go so far as to specify the primary failures to tolerate is 3. Now I'm going to have a minimum of 7 ESXi hosts. And for every 100 gig object that I store, it's actually going to consume 400 gigs of space. So it's a significant amount of overhead in order to get this level of redundancy. But now you can see here, hey, I can lose any 3 hosts. Let's just pick 3 at random. ESXi02 fails, ESXi05 fails, ESXi04 fails. Great. I still have 2 intact copies of my virtual disk, and I still have a majority. 4 out of the 7 objects are still available, and therefore they can establish a quorum, and my virtual machine can continue to function. So with RAID 1, what we're basically doing is straight up mirroring. So as you'll notice in all of these models, the bare minimum, even for failures to tolerate equals 1, we're still consuming double the space. Failures to tolerate equals 2, we're consuming triple the space. Failures to tolerate equals 3, we're now consuming 4 times the disk space for each object. So it's getting a little bit expensive here. What if we're on an all-flash vSAN configuration? And I want to do failures to tolerate equals 1. Now I have the option to do that with RAID 5. So with RAID 5, the mechanism works differently. It works just like RAID 5 does on a shelf of disks. Exact same redundancy method using parity and data bits. But now I've got failures to tolerate equals 1. I've got the same level of redundancy that we saw in our first slide, but it's only consuming an extra 33 gigs of space for my 100 gig object. Big space savings here. I've got to have a minimum of 4 ESXi hosts in order to run RAID 5. And they have to be all flash. Hybrid is not supported here. Same with RAID 6. They have to be all flash, but with RAID 6, the big benefit here is that my failures to tolerate jumps from 1 to 2. It is going to cost me a little bit of space here. Each 100 gig object is going to consume 150 gigabytes of space, but it's still way more efficient. So that's how my vSAN objects are stored on my cluster. And again, it largely depends on the RAID method you've chosen. Just bear in mind, RAID 5 and RAID 6 are definitely much more space efficient, but are only available in the all-flash configuration.